Yeah, another draft physics video production presentation. Still. Anyway, first we'll dispense with a stupid comment first, and then get on to double slit stuff. So it's just going to be about light some more, and it's a sort of an important subject, understanding how physics took the wrong road and all of that. So we'll do some more of it. So anyway, so some guy called Guy. How can it be a troll account where you're the only account going by the name DraftScience? So you don't understand how they can spoof YouTube. They use whatever hidden characters, ASCII 2 bullshit to create a name that really isn't that name. It's really a bunch of other artificial characters, and YouTube converts it into plain text. It's like those stupid emoticons people post in their video titles. It's not real, it's fake text and blah blah blah, little tricks they allow. And so that nonsense gets abused to make fake accounts, and they don't do anything to stop it. And it's a systemic problem. I mean, if you're an accountable person making videos for 10 years, YouTube censors you and blocks your videos and terminates your account. But if you're some stupid troll, they'll do everything they can to protect you and allow you to just do this reckless slop on the internet, because it creates, I guess, more interest, and they get views from these trolls, and the trolls watch the ads and all that kind of crap, so they don't want to discourage the trolls, apparently. Now, that becomes obvious. So you could say, come on, this is just too easy to point out. Well, it's too easy for me to point out. It's not my fucking account, okay? And if you did something like view the icon, you can do that, view the little image, you'll see it's not exactly my image. If you view my image and you view their image, you'll see it comes from different locations, it has different IDs in it and all that kind of crap. So I guess there's some way you can do it. But the fact is that YouTube has made it really easy for these fakers, and I'll point it out. File not found. Interesting. Anyway, so here's a live chat room, right? And so I don't know if this is what's happening for everybody else, but I can't view their account anymore. You can't click on their icon, you can't click on their name, and when you go over here, it used to say go to their channel, and they took it away. I mean, it's even on YouTube's help videos, they show it and it says go to channel. Well, why'd they take it away? Why did they take the go to channel away? Because it's the only way to see the channel, right? I mean, it's the only way to do anything. So unless you people actually do hit this report or block thing, report anyway, these fucktards will get away with it. And even if you hit report, it doesn't mean anything, because the choices you get aren't very good. I mean, it's not hate speech. It is harassment, I'd say. When somebody's stealing your identity, that's pretty harassing. But they ought to just say stolen identity, because it's so pervasive, a thing that happens on YouTube, where people steal people's icon and then steal their name and pretend to be them in a chat. And it's just disgusting. And you're telling me, you have some sort of evidence it's me. I've told you clearly, okay, it's not me. I don't comment in live chat rooms, asshole. And so the easy proof is that I'm sure the fucktards who got little wrenches in Superhuman Dance's retarded fucktard asshole room, I'm sure those little shithead wrench people probably can go to the channel, and they can see there's no videos there, and that it's not a 10-year-old channel or any of those facts. So fuck you. I mean, if you're going to accuse me of lying, then come up with some fucking evidence that I'm lying, you fucking shit. You don't have any right to call somebody a liar when you don't have any evidence at all. I mean, none, zero. So fuck you. It's just such bullshit. It's bad enough they let these trolls loose, but then you assholes sit there and feed them by making them win. Oh yeah, it's really admitted. No, it isn't, you fucking losing stupid idiot. Fuck, I have nothing to discuss with Superhuman Dance except what a deplorable fucking scum as a human being he is. So if he wants to have a conversation about how deplorable and ignorant and awful he is as a human being, well then fine, let's have a debate about what a piece of fucking scummy lying crud he is. But anything else, he's not qualified to have a debate on the subject because he doesn't know fucking anything. Shit. All right. So I don't know what to tell you. So I would be curious if other people have seen the same thing, where you can't go to the fucking channel. You can't check on any of these fucktards to see if they really are who they say they are. You can't do it in the chat. So until he posts a comment in a real comment section, yeah, there's no way to do much about it except to hit the, report button. And one of you assholes has to do that. I've already tried it, and YouTube doesn't pay any fucking attention. So, yeah, they get away with it. Because YouTube sucks. Because it allows fucking lying scum like you to just be lying scum. I mean, it's really that bad. Just give the lying scum license. Alright. So, on to the other crap. Which isn't this crap. How did I end up in the wrong place? I don't know. Well, anyway, somewhere over here is the crap I want. Let's see. Young Theory of Light. No, wrong one. Wrong one. Two Slit Veritasium. Yeah, that's the right one. This one should be the... Nope, that's just not right. Where the hell did the Joe Rogan shit go? Oh, there it is. Okay. So we'll start with this and move on to some other stuff and eventually end up with Yale professor again. And that's going to be a long video, so I'll probably have to go a couple of videos to get through it all, because it really does get the whole history of quantum mechanics and the whole history of why they drew these conclusions. And it just becomes obvious, that they jumped their evidence, and that's all that took place. They just wanted an answer a little faster than the answer was coming from the facts.
Marble. Let's fire a stream.
He's already shaking his head, folks. It's not a tiny marble.
Yeah, it says you, Sean Carroll. So this is the Dr. Quantum video. So they play the Dr. Quantum video for a physics professor, and he doesn't have enough knowledge to say this is just a religion. They're trying to use science to defend religious perceptions of reality, and it's just absolute nonsense. It has explanations that aren't part of any real history. These detector experiments were never performed. You can't use them as an argument.
We're gonna do a little bit of commentary on it. We can't just play the whole video.
Right.
Okay,
right.
I can do the. I know exactly what they're talking about.
Okay.
It's a very famous experiment. So
Yes, it's a very famous experiment that's completely misdescribed by all the physicists.
yeah, so if you have two slits that you let marbles go through, they get two slits in the receiving screen on the other side.
Right.
Whereas if you
So we know that that's not even true, right? That we know that some of the marbles do actually bounce off the slit and go in all kinds of funny directions. So you won't just get two slits of marbles. So that's right there is, they can't even say this part right.
let a wave go through two slits, you get this interference pattern.
No, you get two waves is what you get. And then you have to explain, okay, that, in a medium, those two waves will interact with each other because it's made out of physical matter. It's a medium. And the matter is connected to each other, the little corpuscles of the medium, and they drag each other with each other. And so if two of them are moving in two different directions, one's going up and one's going down, they'll cancel out each other's motion because they're connected to each other. But there's no evidence that forces do that.
Right. And so what happens when you let an electron go through? The answer is you get an interference pattern. It's more...
Right, so we know that the real experiment started with photons, not electrons, and the electron experiment is a completely different experiment in a sense, because the electrons are, as ironic as it sounds, right? This is always something to understand about these experiments. So waves are gigantic atoms. Sound, water waves is atoms, sound is atoms, okay, big things. But let's just, for the record, understand that photons, we already know they have a polarization, right? Okay, and the polarization is proportional to the wavelength, because what it's really proportional to is our frequency, you could say, is that it's proportional to the speed of light, frankly. And so the speed of light is deciding both things. But regardless, so the polarization is, the average visible light, 500 nanometers, whatever you want to make it. And again, nanometers are billionths of a meter, very small thing. And they keep saying that the slits are proportional to the wavelength, when no, there's 1,000 wavelengths in here, in this slit. So they don't even get that right. I mean, it doesn't make any sense by their own jargon. They should be able to get at least the size of a nanometer correct in proportion to the size of a millimeter, which is 1,000,000. But anyway, a million nanometers in a millimeter. But anyway, so this is rather huge. 500 nanometers doesn't sound big, but it's actually very huge compared to the size of an electron. An atom, the whole atom, is only 0.5 of a nanometer. Okay, that's for a whole atom. Okay, so we're talking electron is like 0.0000005 or something. I mean, it's a tiny thing in space. It takes up an amount of space that is so infinitesimally small. So even compared to the polarization of average light, an electron really realistically would be imperceivable. I couldn't make the dot small enough for me to represent how small an electron is by comparison to the size of a photon, in dimension. However you want to perceive a photon. I mean, the frank truth is that you have to recognize that it's a big thing, okay, in terms of its, however you want to look at it, its wavelength or its amplitude, that is the space it takes up as it's in its polarization. So that's just so clearly, to make slits small enough that electrons have a hard time getting through them, technically, you have to make them insanely small. And if you make them insanely small, you can just imagine that the electron, what is it really going to hit, or what it's going to interact with? How does it know where the slit is? See, this is the part that it's so, their physics, they don't ever talk about the material of the substance. And we already know that the atoms of any surface are atoms. Okay, there's no surface, there's no wall here of a surface. There's atoms with electrons and protons, right? Protons and electrons and electrons and electrons. We know that that's what's on the surface of surfaces, is electrons. And we know that the two kinds of material, like this stuff on this side, the atoms in the atmosphere, that we know that the atmosphere has, what we call these little free electron-y things that are loosely associated with any protons that are going to be anywhere. And you're always going to have these electrons that are barely attached. They're just, hanger-oners, just floating by and saying, oh, there's a proton over there. Oh, but there's electrons guarding it. So they just hang out outside the gate. And so this is what the electron has to travel. If I make a tiniest slit, that it's going to charge. I mean, one side has to go negative and one side has to go positive, or they wouldn't be compatible. So, I mean, the electrons on this side are going to switch over here, and the protons are going to move in here, and so now it's going to be a positive side, and this will be the negative side. And, so you got a real problem because you're putting something charged through the slit. And then when the electrons are flying through space, they hate each other. I mean, they really do hate each other, and they're going to migrate away from each other. And, there's going to be a tendency, just through that process of them ending up, in clumps, by accident alone. They can't, theoretically don't have enough space to work with or time as they're moving to be able to sit there and arrange in any perfect way. They have to just arrange in the sense that I don't like you, and one moves out to the outside. So they're spreading just by the fact that they don't like each other.
like a wave than a particle. But the real weird thing that they're going to get to eventually is if you let an electron go through two slits, but you put little detectors on the slits.
Okay, so you're just saying, where's the credibility here, right? I mean, he's explaining it to other people by bringing up subjects that are just ludicrous. There is no way to detect an electron in a passive way. You can't shine light at an electron. You just can't do it and see where it is or not interfere with it completely. So there is no detecting any of this nonsense. So the electron is, there's just no way. You can't hit it with a photon or a piece of energy. Right now, obviously I'm not saying you can't hit it with a photon anyway, because the photon is a whole bunch of these little things. Not a whole bunch, but at least 6 of them for us to see it. And they're spread out over the entire polarization. I mean, come on, we've already been over all this crap, and only one little bit of the photon has any chance of hitting an electron. But we know when it does, what's going to happen is, no matter, depending on how the electron is adhered to the world, because it's always adhered to something. Electrons just don't sit somewhere free. They're charged. There's always a bias for them to move in a direction. There's always a planet Earth closer over there, or there's something closer. And they're going to always drift that way. They just can't help but be attached to matter. They have to get to protons. That's what they're going to find. Whatever side of the universe they're flying through or just sitting by, one side's going to have more protons closer to it than the other side, and it's going to go that way. So there's no such thing as like a bunch of electrons just floating around being casual. There's always a bias, and they're always moving in a direction. And as they get closer and closer, they move faster and faster, and there's just no way you're going to find electrons just hanging out somewhere freely. But regardless, when one of these little quantas, one of these bits of energy, as Einstein pointed out, hits an electron, this is not a debatable subject. The electron has a tension. It has its own momentum. It's either sticking to a surface or it's moving towards a surface. It's always moving towards something or it's stuck on something, but there's no such thing as I'm just free sitting here being still. There's no such thing as a still electron that isn't tied to something. And so you can kind of understand, if I have it tied to a tether and I hit it, well, it can't go this way because it's tied. So it has to do this way or some other direction. And the photon's energy, is in a sense absorbed by this motion. But it's not really. This motion will stop when another force hits it, drags it to a halt, and then when that happens, the electron has a new position, and the new position will reflect a different universe to the world. The world will see the difference. And they'll see the difference because of the energy being reflected off the electron in moving its position, and that's essentially a reflection. But anyway, so that's the theory. The theory would be as the photon's energy is changed, but it's not really changed. It's just that this distance will be added, to the frequency of these little bits. It does slow them down just a hair, and that little bit of slowdown is enough to change their phase, their frequency. But it's such a tiny amount of difference from one electron that you can never perceive it. It's like going from 500 nanometer light, frequency-wise, to 500.0002. It's a tiny change in the total energy for one of these little encounters. So you need quite a few of these encounters before you start really reducing the energy of the photon. Compton scattering kind of stuff, which is a whole nother subject I have to get into someday. So anyway, so obviously the surfaces have electrons. The electrons will deflect the energy, in the sense the electrons will not move forward. They'll move at some angle. They'll scatter the energy. Alright, but there's no detecting an electron. You can't hit it without moving it. It's energy. Photons are force.
So you say which slit did the electron go through? then it always says it goes through one or the other. It never goes through both.
So it always says there's no experiment. There's just none. It's not been done. It can't be done. There's no theoretical grounding for detecting an electron without disturbing it substantially. So there's no way to do it. He's a theoretical physicist. He should know there's no way to do it. So why am I arguing that somehow it was done? Oh, because that's convenient. Not because it's true.
And the interference pattern on the other side disappears. You only...
So more says you, right? It's not, they never did the experiment, so they can't say that's true.
You see the two lines that you would have seen if they were marble-like. So the point is, when you're not looking, the electron is
See, there's no reason to believe that looking would make the photon straighter. There's every reason to think it would just deflect it more. So, you know, they, like I said, they never did the experiment. It wouldn't make the pattern look cleaner. It would make it look messier. And it would probably spread it even more.
acting like a wave, and when you look at it, the electron acts like a particle.
So this is just more bullshit when you look at it. The only way we observe it is through its collisions. Period. It's all how we observe all of these subatomic particles, so this crap about looking at it is just that it's frickin' crap. And physicists shouldn't be allowed to keep saying it like it's a reasonable thing to say. We don't look at anything. We frickin' interact with it in a substantial way. We can't touch it without squeezing it and busting it. It's so fragile compared to anything we can throw at it.
Right.
That is the lesson of the double slit experiment.
Right.
And the lesson of the double slit experiment is this is why physics has no credibility, is because they can't tell a story about a simple experiment, simple, really crude, simple experiments, and they can't even get those stories right. So how can you trust them when something like LIGO happens or something like Higgs boson? You can't trust them with the simplest experiment to get the facts right. So why are you trusting them when they say all this other crap is going on?
Why?
Why? Because when you put that detector on the slits, you
Didn't happen.
interacted with the electron and you localized it, right?
You didn't do any of this crap because you never did the experiment because nobody's stupid enough to think they could do it. I mean, again, you can't even make slits that you can throw electrons through that are neutral slits. It's not possible to make those two neutral slits that close together. That's the Casimir effect. I mean, you already know you're out of luck to be sending an electron through something called a neutral slit. Can't be done.
There was no such thing as the position of the electron. There was no such thing as the answer to the question, did it go through one slit or the other? There was only a cloud. There was only a wave.
Yeah, so that's all just made up, okay, to play a little math game, and the math game isn't that sophisticated, actually, and isn't that accurate, as can be pointed out. So again, this is just such mush, and they get away with it because there's nobody calling them. Not one of these physicists will stand up and say, yeah, we're just telling stories. It's really just stories we made up. This doesn't have anything to do with us having real evidence for any of this crap, that things aren't where they are.
Going through. But you affected it, or whatever the detector was, affected it when it looked through the slits to see did it go through this one or this one. And that effect changed it from being going through both slits to being only going through one.
And how does it affect it like that?
Well, it's what's called quantum entanglement.
So this is where the guy's saying, what does entanglement have to do with it? Well, this is where they make entanglement have something to do with it, is because they're saying that somehow it turned into some whatever multi-electron and is now in two places at once.
Detector becomes entangled with the electron, and this is where you get into my favorite version of quantum mechanics, which is the many worlds interpretation. The right way to think about the electron was that cloud, that wave going through. That's the natural thing. The weird thing is that when you look at the different slits, you only see it go through one or the other, and it acts like a particle. So how do you explain that? So in other words, our natural intuitive way of thinking about electrons is as particles, little marbles, and quantum mechanics.
It's not the natural intuitive, it's what all the evidence points to. They're shared, for fuck's sake, by atoms. How can something share something that doesn't have a position?
He says, no, no, no. It's naturally a wave. The weird thing is when it acts like a particle. And if you're a many worlds person, what the answer you give is the following. When you look to see, did the electron go through one slit or the other, you, or whatever video camera you had or whatever, becomes entangled with the electron.
Right, so when it lands at all the locations, and we created 7 zillion universes. I mean, all the possible locations. It actually did land at all the possible locations. You roll the dice and everything turns up. Okay, boxcars, snake eyes, 7, 11, everything turned up. Everything happened. You do the roulette wheel and you roll the ball, and the ball falls into every single number. And you just make a new universe to account for. and nobody just laughs at this and says, what the fuck? You're just making this crap up. We know that's not how it's working. Come on. This is too silly. And the fact that you people won't just say, too silly. This is terrible. There's no point in going in the rest of many worlds, right? I mean, and he's already premised the argument on false notions of fake experiments. Again, it's not even reasonable to theorize about slits you can shove electrons through. It's not even theoretical that you can make this neutral slit. Alright, so this is the old Veritasium 1 photon at a time thing, and I just thought I'd say I remember it having all this noise in it. Like 50% of the photons are in this bottom part. And but now that I think about it, that's perfectly consistent with what's really happening, is that the actual events. See, the problem with this Veritasium experiment is, he's basically measuring the incidence of, so he tries to create a very weak photon source. Okay, so it only sends a few photons at a time, and then it goes through the 2 slits. And the problem is he's using this detector that's really close, and what they're basically doing is just moving the detector across and back and forth to measure how many photons. Alright. And the problem is it's only 5 millimeters of whole movement, so he's only moving this point, right? No, 5 millimeters, okay. Yeah, so about it's 0.5 centimeter, right? So a half a centimeter is the entire movement of the detector. So you can tell this is really close to the slits, and it's not a really great idea for that reason, alone. And they're moving it on, it's not big enough to even get the whole pattern. So it's the double slit pattern, and depending on how you have the slits, you can have 11 notches in the center part, right? You can have 11 things before you get the dead space, and then it starts again. So you can have you can have more than 11. I mean, 11 seems to be the most I've seen. I think 13. But anyway, you can get a lot of little bars in there, so obviously he didn't go far enough to really get the picture. So, but the point is that all that noise isn't just noise. What that is that's the envelope. So you have the envelope pattern, and the bars are inside, on top of, essentially added to the envelope. So they're up here. And you get the vision of that. You get half the light is here. Okay, half the constituents. So they're coming from the middle impediment is shooting the light to this whole range. And then the 2 outside slits, you can still see that, right? Yeah. They're the ones making the little bars. I mean, this is not the right, they would obviously be going both in the same direction to be making all the bars going this way and then all the bars going this way. They're going the same directions. But they're the ones making the little bars. So the 2 outside slits are controlling the added light that will be the bar. And the added light, and the added light, and the added light. And in most cases, you'll never get a full dark here. Okay, because you're really just adding light to make the bars. So the bars are half as dim if you did them all by themselves, because you're adding half the photons are in the underlying support photons that were produced by the 2 interior slits. So it's a composite of the 2 patterns, and that's why you have a 0 here, is because neither this these angles don't produce in phase lines, nor do these two angles produce in phase lines. So you have nothing in phase here, and so you have nothing, and the rest of these are, you know, additions to a weak amount of signal that was produced by the envelope. So the envelope produces a weak signal that you probably wouldn't see if it wasn't for the added signal of the bars. So just pointing it out. I mean, I did remember that. It is as I remember it. So if they had expanded, if they had done this thing more than a half a centimeter of jiggle, I mean moving, if they had moved it further, they could have seen where it really tapers off to a real zero photons. But they didn't do that, so not very useful. All right, I don't know if I'll go to him or do this one first. So this is another guy, another professor at some college. So he goes through this whole video doing the standard crapola, you know, the standard bad, cheap math, okay, that just produces a bunch of bars, bar, 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 no cutoff in the pattern. None of that is explained by this math, okay, so he just keeps throwing through all that crap. It doesn't, you know, like I said, it has nothing to do with the real pattern. So he goes through the whole video doing that, well, the whole explanation that way. And then when he gets to this part, see, he just has hump, 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 hump. No dead spot, none of that explained. So this is just the old theory that it doesn't explain the real pattern. And then he actually displays the pattern on the board, and he's still talking about it because he keeps the lights on so nobody can see all the extra fringes. So he just has it with this little spot here, and he's explaining on, you know, how the math works. And then, okay, at least he has the integrity to step up and point out how, oh, well, that's really all a pile of crap.
The wavelength is about 0.6 times 10 to the minus 6, 12, and then you get times 10 to the minus 3.
Okay, we'll move on. He's just
Well, it's
doing
true
that.
for small angles. For larger angles, who knows what happens.
I'm just doing the obvious reverse calculation that once you know where a location is, you can figure out where these two lines are in phase, and then you can tell what the frequency of the light is. Alright, so we're just moving along. So this is, I think it's right in here somewhere he points to it. Okay, well, we'll just play this part.
Then you might say, now wait a minute, that's still a pretty small angle, right? If this thing's 5 meters away and I'm moving just a few centimeters, our small angle approximation didn't break down. Something else is going on. Well, what else is going on is that these slits are not infinitely thin. It doesn't really throw its light evenly all the way around half a circle. That would take an infinitely thin slit. What we're really dealing with here is diffraction.
So it's hilarious, right? It doesn't do something even, which that it can't do something uneven. Okay, it's a single slit. It does something quite even. And then he says the word diffraction as if somehow you can just throw the word diffraction out and that somehow changes the wave shape or something. There's no way to change the shape of the wave.
So diffraction defines how the light will spread out when it goes through a finite slit, or a really thin slit for that matter.
So again, these aren't finite, really thin, all of this rhetoric. Again, these are really big slits in the sense that a half millimeter slit is thousands of wavelengths are in that distance.
So that's part of the reason it goes down. And then you can actually see something else. It goes away and then it comes back. So let's turn the lights out and see.
So he just did all of this math for a pattern he concedes isn't correct. I mean, can you just see how does this have any credibility? He just spent, whatever, 17 minutes explaining this little simplistic two-wave description, right? Drawing the two interfering wave kind of nonsense. And then he's basically going to concede, no, well, that's not the right pattern anyway.
What's really happening. All right, so now let's have a closer look at this. So we had our pattern, and it goes away because of diffraction, but look at this, it goes to 0.
let's see how many we got here. Let's see, start over here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. You know, that's the popular number.
And then it comes back. Now, this is pretty dim, so we're going to put one of the cameras really high sensitivity so you can really start to see it. And then, so we have it, it's back, and then it's gone again. Here, look at that, it's gone.
So it might be 13 now. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. There you go.
And then it comes back. And then it's gone again, and it comes back.
Right, so not in your mathematical description. It can't be illustrated by two spherical waves, symmetrical waves. So wave theory doesn't do this at all. It's a bad explanation because it's just a huge flaw in it. I mean, a really big flaw.
So through this whole pattern, it's actually keeping the cosine that we just calculated. It actually does do the cosine way out, even to as long as the angles are small, but it's being modulated by this other function. Well, the other function is diffraction.
Right, so the other function is going to call diffraction, which is just silly. There's nothing in the definition of diffraction that accounts for on-off patterns. Okay, it's not in the definition of diffraction. Diffraction is about spreading. It's not about spreading in some bizarrely uneven way.
And we'll be calculating that in the next learning sequence.
So he says he'd be calculating the next sequence. That probably means when he does multiple slits, because then he'll change the whole mathematical paradigm. It'll just change entirely, use a completely different kind of mathematical analysis that'll really be saying how many surfaces are there. So the 2-slit experiment that was 2 waves will end up becoming the 4-wave experiment, in the sense that there'll be now 4 sources, and the problem is the sources are going to be not in the center of the opening. The sources are going to be relevant to the surfaces, and that's going to be the place where it's actually the actual function is.
So we have derived a nice little one-dimensional function for the irradiance, and we have demonstrated.
Right, and it's not even accurate because frankly they've derived the all they did was do the one pattern, that is the little bars, and they just forgot about the envelope. And they did it by just averaging. So they've taken an average where they've taken the point in between the slits, which would be an average of the distances. That is, it'd be an average of the distance of the impediment and an average of the distance of the width of the slits. And since both of those numbers aren't in the formula, that is, they're not in the math, the distance of the outside surfaces and the distance of the inside surfaces aren't in the math. So obviously they can't know about the external surfaces, and they're just approximated. So the whole thing is an approximation. It's not accurate. And it really depends. It can only be accurate if there's symmetry between your impediment and the width of your slits. If you don't have symmetry there, it won't give you a good answer. It'll give you a really bad answer to where those locations are. It'll get them wrong because the math isn't right.
Created a nice little one-dimensional irradiance. But you may recall.
All right, so he didn't do the more complex math, and so then he does this little spray can thing, which is a nice little demonstration, but it's not worth much, but it's
Right down here, right where the beam is about to hit us in the face, right. Oh, there it is. Yeah, there it is. And then I'm going to spray this into the beam, and we'll see what we get. So here we go. Oh, sorry.
jokester.
That's not bad.
Yeah, college students need that.
Let me spray it the way it's meant to be sprayed, which is away from the face here. And if you look at this, you can really see the full pattern.
So, I mean, quite obviously, yes, where the little bits are going to make new photons. They're going to reconstruct them in all these locations, and the locations will basically point out that this really is about geometrical vectors. And so, of course, the pattern, as you got closer, would be in the same, they'll all be in different locations in one direction, and the other, they're in different locations, but they're different locations that are symmetrical to the point sources. So, yes, perfectly consistent with what I've argued. But anyway, just glaringly bizarre video in the sense of just pointing out how, here he goes through this whole thing on an assumption that the pattern is some symmetrical pattern, when he knew it was an asymmetrical pattern and all his symmetrical waves can't produce it, and yet he doesn't account for that in any way. So really quite mushy. Alright, so what else? Yeah, we're going to do that. Are we ready for that? I guess that's where we're heading now. Alright, so this is going to be a lot of stuff. So it's going to take a while to get through all this, because he just really connects the whole reasoning for quantum mechanics. And again, you can see the glaring places where there's these huge assumptions. I mean, one of them I'll illustrate now just because I feel like it. Yeah, because it's something that's come up before. This is always the argument people make, is that when they do see this two-slit pattern, I'll draw it this way. We'll only put 4 in the middle. You know, they make this argument that you know, you have this 2 slits. Well, that's not very proportional. Alright, so you have the slits, and there's this argument that if I covered one of these slits, okay, there's going to be light in a certain location. And then if I cover the other one, open this one and cover that one, there'd be light in a certain location. So there's definitely light in all of these locations. And that somehow, okay, when I have both slits open, I'm getting a dark here. Okay, and I get a dark here. And I get a dark here. And there shouldn't be any darks there because, I mean, frankly, I mean, it doesn't make any sense, right? I mean, I have light, and then and there's light here, and then I do this, and there's light here. Well, how does it get dark? You know, and that's just an assumption. There's no, like I said, if they do the experiment, they'll see that that's not what happens. And I showed in the other 2 videos, so I won't show it again. But you can see in the patterns that you'll see there's a lot of bleeding between the spots. And that what you're not really getting a pure dark between them, a real hard dark line. And if you do get a hard dark line, the argument is you never did the experiment where you got that hard pattern where you actually did see this. So this wasn't enough light to create this pattern. The light was spread, and by being spread, it's weakened, and you wouldn't see this pattern. So what's really happening is the bar pattern is always on top of this. So that it doesn't really, there aren't any true darks here. You'll see the true dark here. This is where it's going to be dark. Okay, but it's not going to be dark in between these bands. It's really just adding more light. And so it looks like it's light and dark, but there's no true dark here. It's not absolutely zero. And as that Veritasium image shows, there's no absolute zero. It doesn't, the pattern doesn't go all the way to zero, all the way to zero. The pattern is really just on top of an existing amount of light that's being produced by these 2 slits. So these 2 slits are producing this light, and these 2 slits are producing the little bars. The wider you make the surfaces, the smaller the profile, the narrower you make this, shorter the distance. See, this distance is big distance. This distance is small distance. Small distance means wider. Big distance means little. And that's all that's taking place. They're just 2 patterns created by 2 different sets of surfaces at a distance from each other, and those distances are key to creating these in-phase markings. So the longer the line, essentially, the longer the distance, the more notches in the ruler. And therefore the smaller the location where the notches line up. So it's really that simple. Particles do explain it. You just can't think of the particle as being photon like this. No, it's photon made of quanta. 6 of them. Again, they never talk about the length of a photon. And why don't they do that? because then they'd have to acknowledge that there's nodes, and that the nodes are just quantities, that's a little clump, 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 that a photon is a series of clumps of energy, not just one clump of energy.
So this is a very exciting day for me, because today we're going to start quantum mechanics, and that's all we'll do till the end of the term. Now, I got bad news and good news. The bad news is that it's a subject that's kind of hard to follow intuitively, and the good news is that nobody can follow it intuitively.
So this word intuitive is a little bit, all there really is simple and complicated. You can have a simple understanding of something, one that's and one that's been well established by many different times. Just step in dog dew and it smells like dog dew and it's hard to get off your shoe. So you have this intuitive understanding that of what dog dew is. And yeah, there could be examples where it doesn't fit, like really dry dog dew or something. But generally speaking, your reaction is don't step in dog dew because it's probably not going to be dry and it's going to stick to your shoe and it's going to smell. So you have an understanding. But I'm just saying, to say that's intuition is somehow a different thing than the more thoughtful thing. It's really not a different thing. It really shouldn't be that dramatically different. Your intuition should be compatible with your more complex analysis. And when they're inconsistent, you got to make a concession that intuition is trying to make something complicated too simple. So I would argue that they're intuitionally using words like particle, and it really just doesn't fit because they haven't defined what a particle is. So when they say particle to you, they call something a ton, they've given you an impression of what that is, like it's some sort of confined thing. Like even a human being can be described as one of these particles, even the moon with all its chemicals and all its compounds, its dust and its rocks and all kinds of stuff, but no, we're going to call it a particle, a thing. So this is where the logic breaks down, and it breaks down too in not understanding that the electron is a little tiny thing, that the photon is, the quanta in it is very small, okay, but the thing itself, the spread over which the photon is realized, where it actually does hit a surface, is a very large area, okay? It's not a little thing, it's a big thing by comparison. And again, we'll call this as a photon, right? I mean, this, all right? A photon, even if you go with your silly wave crap, you're stuck with the idea that this is, whatever the double helix. Even if you're going with that, you do understand that this isn't a photon, two of these isn't a photon, that it takes a certain number of these to make a photon. So it's not a particle, even if even if you're going to do some intuitional argument and say, I'm going to try to think of a photon as a particle, well, you're forcing the particle to be a kind of a strange beast where it has this polarization this way and it has wavelengths this way, and you're going to require numerous wavelengths in one direction and no change in the other direction. So, I mean, you're going to have to make the particle into this projectile. You might as well put a little bullet head on it, maybe a little fiery jet coming out of the back. I mean, it's not exactly a particle. So, I mean, there's no continuity in the vocabulary, and that's what breaks the intuition. But the intuition is consistent. I mean, you can understand that, okay, this is a clump and this is a clump. A clump separated by a distance. You can understand that, separated by a distance. Okay, that's a frequency. And then if I take one of these clumps and I put it a little bit out of alignment, and put another one out of alignment, well, you can understand, okay, that's polarization. That's easy to understand. So I still have my wavelength. I still have them. Two of them are traveling in phase, where their clumps are in the same locations. That's all consistent, right? So you can understand that, but you can't do it like by intuition. I can't just say a composite particle. That's not going to get you too far. I mean, that's what it is, but I mean, I can't just say that. I have to illustrate. I have to show you what the thing is. So intuition isn't going to work if you're just going to use words like wave, right? I mean, waves do this, Waves break and attempt to reconnect. Okay, waves are, again, you can understand them as molecules stuck to each other. So if I move this molecule, the other ones are going to want to go with it. That's what waves do. So if I say wave versus particle, and then I say, well, we're going to describe light, gets kind of messy because, like I said, you're not going to find evidence of this adhesion between photons. And then you're stuck with your ether, your field theory of glue, that somehow the photon's traveling through glue. And how's that going to intuitively work? I'm saying it just can't. You can't draw that picture.
Richard Feynman, one of the big figures in physics, used to say no one understands quantum mechanics. So in some sense, the pressure is off for you guys because...
Yeah, so, and he also said, quit thinking about it, just do the math. He also said, if you don't like it, tough, to the idea of God playing dice with the universe. I mean, he said a lot of things that are just knee-jerky, kind of sloppy. They might satisfy your intuitional problems, in the sense that he's just giving you an excuse to not be distracted by the inconsistencies of the theory, that it doesn't make any sense, that they can't draw a rational picture of what they're saying happens. They can't draw those two symmetrical waves coming out of two openings and make them create the actual pattern. They can't draw it because it doesn't work.
I don't get it and you don't get it and Feynman doesn't get it. The point is, here's my goal. Right now, I'm the only one who doesn't understand quantum mechanics. In about 7 days, all of you will be unable to understand quantum mechanics.
Right, so they make a joke out of the fact that it doesn't make any sense and it doesn't really add up, and it has all kinds of inconsistencies in it, and it's underdeveloped. It doesn't explain everything. It doesn't work. You can't apply any of the principles consistently and get away with it. It won't work. So you have to apply Huygens in one case. In another case, you just say, Huygens doesn't happen. You have to break all kinds of logical rules to make it work.
And go back and spread your ignorance everywhere else. That's the only legacy a teacher can want.
Yeah, that's the only legacy a teacher can want, is to talk a bunch of goofy crap, make a joke about how it's goofy, and still get them to buy it. So this is like a religious class, right? I mean, okay, I'm going to tell you a silly story about a god that poofed out of nowhere and had some dopey notion of making humans with belly buttons and fucking gave man boobs for no good reason.
So, all right, so that's the spirit in which we are doing this. I want you to think about this as a real adventure. Try to think beyond the exams and grades and everything. It's one of the biggest discoveries in physics.
I want you to think about it. See, they didn't discover, they just made up. And so it's the biggest made up travesties of physics, that it just made up this crap and it won't let go. It just, it's got a hold of it, it's dependent on it now. It's like an addict, a heroin addict. He's got to put heroin in his dinner. I mean, it's just stuck with this wrong notion of reality, and it can't let go.
In science, and it's marvelous how people even figured out this is what's going on. So,
no, it's terrible. It's sad. It's tragic that you all accepted mushy explanations, bent space, whatever the hell that would be, when it doesn't even work as a three-dimensional model. You already know it's out of business as a model, bending something in 3 dimensions. It doesn't work. It just turns into a convergence. It's just a vacuum cleaner. You're just saying there's a little vacuum cleaner inside of everything. I mean, it's silly.
I want to tell you, in some fashion, but not strictly historical fashion, but purely historical fashion is pedagogically not the best way, because you go through all the wrong tracks and you get confused and a lot of battles going on, and when the dust settles down.
So if we fuck up the history, then I can make the history sound more rational, is all he's just saying. If you do the real history, then you'll see, oh, okay, so these guys just made all these weird assumptions. And everybody just said, I like that guy, so let's go with his assumptions. And then you have silly frauds, essentially, where the Eddington experiment and nothing, poorly done, poorly, not by the fault of the scientist, but just they got very poor results, and they just decided to sell it as a real experiment when it was a piece of shit.
A certain picture emerges, and that's the picture I want to give you. In a way, I will appeal to experiments that were perhaps not done in the sequence in which I described them.
Or not done at all. and that's the big joke. They're experiments that we fantasized about but never really did, and we just made up the results of the experiment. The detector experiments, for example.
But we know that if you did them, this is what the answer would be, and everyone agrees. And they're the simplest experiment.
Yeah, we all agree. So yeah, that's the whole problem, is you all have agreed to not really care about compiling much evidence. You've all agreed that, yeah, he's black and he's the right height, so he's guilty. I mean, in my opinion, it's that obvious a bias. You just all want this bullshit to be true for some dopey reason, and you're just sitting here finding every excuse to say, yeah, we proved it. He's guilty.
All right. So today we're going to shoot down Newtonian mechanics and Maxwell's theory. So we're like the press. We build somebody up only to destroy them. Built up.
Right, so it makes no sense at all. One minute you say this proves something or this demonstrates something, and the next minute you say, yeah, well, that's not right. So they use it like the guy's last video, right? He uses the wrong math for the wrong pattern, and then vaguely announces that no, we have some other theory that might work, but I'm not going to tell you that one because it's even more convoluted. And it won't show. I won't be able to draw it because if I drew it, you'd notice right away that it doesn't make any sense.
Newton, shot down. Built up Maxwell, going to get shot down. So, again, I try to drill into all of you the notion that people get shot down because somebody else does a new experiment that probes an entirely new regime, which had not been seen before. So it's not that people were dumb.
No, you're doing exactly the opposite. You're still talking about the Young experiment when you know Young didn't see the real pattern, the right pattern. So the whole analysis was incorrect because the pattern wasn't correct, because he didn't have equipment capable of producing what the real pattern is. And so you keep talking about the wrong analysis and you just keep ignoring what we learned from better experiments, is that it's more complicated and nuanced than you thought. But you keep forcing it back into the more rudimentary, simple notion of waves interfering, when waves interfering is something you can draw. It's something Young used the wave table to demonstrate, and yet you can't even draw anything. You can't draw any rational image of your dynamic, because if you draw it, it'll make it obvious that you're not talking about waves. I mean, it's going to be this obvious. If they draw the math that works to describe the two patterns, okay, this is what they'll draw. Okay, if they had to draw it as wave interference, this is what they'll draw. Wave here, wave here, wave here, wave here. Okay, right on the edge of the slits. So the center of the wave is somehow going halfway over the surface and then only partially over here. That's the only way they could draw it, okay, where they could do these intersecting waves and get the two patterns. And even that's not going to work, well, frankly, right? Because the only way they could really draw it is to draw this wave as a big frequency wave, and then this wave as a high frequency wave. This is making the little undulations. Okay, so this is the way they'd have to draw it. And so this wave goes right through the impediment. Okay, and this one, okay, at least it's a wave at the distance, but its frequency is completely changed. So, but that's the only way they can draw it, is to have those two intersect. Have this wave intersect with this wave. Then they'll get the pattern of the two-slit experiment. So they can't draw it, because if they draw it, it makes it obvious this isn't about waves. It's just about vectors. So it's just about light being scattered to all these locations, and the only location you can reconstruct the photon is the location where the distances are a full wavelength. And that's it. They're not a full wavelength difference, anything more or less than a full wavelength, then there's no reconstruction. And that's all that's happening in the experiment. You break the photons going in, you scatter the little bits to all these locations, and all you're doing is saying, okay, I've scattered, this much came in, okay, 50 million little bits, little quantas inside of photons. I just scatter all the 50 million little bits over this entire surface, and there'll be locations where I can put the bits back in order. Okay, where I take fractions of pieces from here and fractions of pieces from here and fractions of pieces from here and fractions of pieces from here, all those scattered bit, and I can put them back together again, and that's where I have light, is where I put the little bits back together. That's what they'll have to tell you if they want to tell you the truth, because that's the mechanics, and that's the drawing that works. Their drawing can't work.
That given the information they had, they built the best theory that they could. And if you give me more additional information, more refined measurements...
Yeah, that's not what you did, though. See, I mean, Young was a fanatic for this wave theory, Huygens, all that crap, and he's promoting that theory. So he just quote-mined essentially the evidence and said, look, this experiment proves it. And then you all started using this proof word, that somehow you prove something. You didn't come close to the burden of proof. You wanted a conclusion, and so you jumped to it. There's no other explanation than you jumped the evidence.
Take to the 10th decimal place, I may have to change what I do. That's how it's going to be. So that's always going to be. For example, in the big collider, people are expecting to see new stuff. Hopefully stuff that hasn't been explained by any existing theory. And we all want that because we want some excitement, we want to find out new things. The best way not to worry about your old theories is to not do any experiments. Then you can go home. But that's not how it goes. You probe more.
Yeah. But you're probing not the elemental experiments, the experiments that'll get you to the truth, or these simple experiments that you never did with enough rigor to get the right answer. You did them casually and sloppily and took the convenient answer, the answer you wanted, and then as you do more manipulations, you find out, oh, there's a catch, oh, there's a catch, oh, there's a catch, and you just run away from the catches. You don't bother pursuing them because they're not consistent with the theory you're trying to sell.
More stuff. So here's what you do to find out what's wrong with electrodynamics, with Maxwell's theory. So it all starts with a double slit experiment.
So again, there's nothing wrong with Maxwell's theory in the sense if you do the math, there's nothing wrong with it because it's all vectors. Again, it's all this geometry of straight lines. Straight lines create all the curved lines. All the curved lines in the charge scenario can all be drawn as straight lines of force. All the curved lines around a magnet can be drawn as straight lines of force between the N and the south, the north and the south poles. And recognizing that the two effects are exactly the opposite. And you can just draw two lines to every point from the north and south pole of the magnet, and you can realize that, yes, all you're going to be doing is drawing lines that represent disproportion. Either the north line is shorter or the south line is shorter, and that'll bend the line. But it's all made out of straight lines.
And you have this famous double slit, and some waves are coming from here. You have some wavelength lamps.
So this is the lecture right after the lecture I already showed where he did this. Right, so he already did this, but he's going to do it again. But yeah, it'll be a little different.
Then in the back, I'm going to put a photographic plate. A photographic plate, as you know, is made of these tiny little pixels which change color when light hits them, and then you see your picture. And that's the way to detect light.
So it's little clumps of material on the photographic plate, little clumps. And the clump either gets hit with enough energy to turn, to flip, or like magnets almost, or it doesn't. So you either expose it or don't expose it. You either flip its chemistry or don't flip its chemistry. And the little bits of chemistry are isolated from each other so they don't bleed into each other, and they just flip. And there's different size little pieces, and that helps make the edges smoother and all that kind of crap. But yeah, it's either enough energy or not enough energy, period, to flip it.
Perfectly good way to detect light. So first thing we do is we block this hole, or this slit. This is slit 1 and slit 2. We block this, and we look at what happened to the photographic plate. What you will find is that the region in front of it got pretty dark, or let's say, had an image.
So it'd be really great if he could actually show real experiments. But he won't show a real experiment, right? Like, they never really did this experiment. They never took a photographic plate and really measured the exact intensity of the light. Like, no slits. See how intense the light is. Put a slit in. See how intense the light is. Put 2 slits in. See how intense the light is. They never even did these simple experiments.
Whereas if you go too far from the slit, you don't see anything. So that's called intensity when 1 is open. Then you
So we already know that when one is open, it doesn't just do this thing. It can do lots of little bars of light, lots of pattern. So again, it's just, how many of these distortions and simplifications that aren't true are acceptable? I mean, how many times can you fudge the truth and it's okay? I mean, should science ever be fudging the truth?
Close that guy, then you get similar pattern. Then you open both.
So you know that these are just a millimeter apart. The similar patterns are going to be right the hell on top of each other. They're not going to be in different locations. So that's all part of the lie here, right? Another falsehood, another misimpression, that shouldn't exist. This should not be misunderstood. These slits are a millimeter apart. Okay, these two objects will end up 1 millimeter apart from each other. They won't be in two different locations in any substantial way. There'll be 1 millimeter of difference between their locations. 1 millimeter, which you're not going to see 7 meters away. You're not even going to be able to detect the 1 millimeter.
Then I told you, you may expect that, but what you get instead, let's see, I got to pick my graph properly, is something that looks like this.
So he just did it, right? He drew all the way to the zero, like the black lines in between these light lines are going to be solid, that there's going to be a real solid all the way to zero. And there won't be all the way to zero if you saw this big hump. So if you have enough light to make this first initial hump from the slit, and it's visible, then you're not going to get an absolute black here. So again, it's just something they made up. This isn't an experiment they did. They don't have any empirical hard evidence. They don't have, you can't find it. It just doesn't exist. They've never done the experiment. They've never opened one, shined a light, judged the intensity over this area of space, opened one slit, judged the intensity over the entire space, open the second slit, judge the intensity over they've never done the experiment.
Now that is the phenomenon of interference which we studied last night. So what's the part that's funny? What's the part?
Yeah, so the part that's funny is the part you got wrong, that isn't accurate. So you talk about new experiments, give you new knowledge, all this kind of stuff. So you've had 300 years since Newton to work on this and do some kind of experiments, and you haven't done any. This is what I mean. This is not hard to do experiment, right? A lab of, a minimum competence has a little bit of money to afford a few photographic plates, because that's the best way to do it. But certainly they could do it with high-tech diodes and all kinds of stuff to, see where the light is actually showing up. But they have to tell the difference between heat and light, obviously, also, though. But, regardless. So he has this really built-in ingrained perception in his head that it actually goes like where there was light, there's no light. And they have no experiment demonstrating that. I mean, I will go back to I really should go back to it, right? This is the math page. That's not going to help us. All the way over here. Is that the right page? Should have been. What the hell happened? I thought it was. Oh, no, that's not the one I was looking for. Not over here, is it? Let's see, stock market, that ain't right. So many things I'm working on. I thought it was here. I must have finally deleted it. Okay, well, anyway, so they've done it where they move the thing over the pattern. Where the hell was this video now? Alright, a little technical issue. That's Feynman. That's it. No, that's not it. This is it. Alright, so, I showed, like I said, it's really an important point, because like I said, he thinks it actually works this way, that where there was light, there's now no light. And what's really happening, okay, what I would argue will be found if somebody actually does the experiment, all right, is that if you have one slit blocked, and let's say it was true that it just created light like this, right? It's going to create the envelope. Let's just make the envelope. All right, so it's going to create this. Well, if I block the other slit, like I said, this is 1 millimeter across here. Okay, this is a nothing distance. And we're not shining the light in directions or something, so there's no this. So if I cover one slit, that's where the line is. If I cover 2 slits, the line is going to be in the same place, essentially. It's just a little tiniest bit off. But you're going to get exactly the same thing. All right, the envelope. All right, that's the fact. I think most people, if they're at all honest, would agree that's what's going to happen. If I block one slit, I get this. If I block the other slit, I get essentially this, the same damn thing. All right, and so the point is when both slits are open, they're arguing that somehow this goes away. This envelope doesn't exist anymore. No, my argument is the pattern they see is on top of the envelope. So they're just seeing this with this on top of it. Okay, and nothing actually goes, this doesn't get darker, and this doesn't get darker. It doesn't go away. The photons that hit here aren't going to go anywhere. So you can't undo them. And all you can do is change the intensity. So if you send a lot of light, then these all sort of blend into each other a little bit. You'll be able to see that there's brightness between these brighter spots. You'll see. But if I lower the intensity of the light, if I go lower and lower, the point would be is that there is a point where if I cover one of these slits, I won't see any pattern because I didn't send enough photons. So there won't be any of this. And if I block this slit, I won't see it because it's too weak a signal. There's not enough photons, not enough little bits hitting. So if I lower the light low enough and I block one slit, I won't see anything. If I block this slit, I won't see anything, and I will see the pattern when both of them are here because really it's a composite. These straight lines are being made, and that's what the math says. They're being made out of the geometry of these 4 vectors. 4 vectors are going to each location, 4 sources. And the 4 sources at these bar locations, all 4 of them, the notches of their wavelength is exactly in the same phase. And that's where the bars will end up being, is where all 4 lines are in the same phase. So it's just a wrong assumption. There is no evidence for what he's saying that it actually gets darker, that any spot on that screen when I open another slit, that I make more light available, that any place on that screen gets darker. Never happens. This spot didn't get darker, right? This spot didn't get lighter, right? When I opened it, I didn't make this spot lighter. Okay, this one stayed dark because it was dark for both of these, no contribution, and these new locations don't make any contribution, so it stays dark. All right.
Makes you wonder is if you go to some location like this, go to a location like this. This used to be a bright location when one slit was open.
So that's what he says, right? So he says it even though there's no evidence supporting that. Yes, it was bright when this slit was open, and if it was bright when the other slit was open, then it's still going to be the same brightness, and you're just going to make it brighter right next to it, and a little brighter next to it. You're just going to make it brighter. You can't make it less bright. So it's just going to stay dull. It's going to stay where it is, like medium, and next to it's going to be more bright, and then there's going to be a medium, and then more bright. But that's all that's happening. You're only adding. You cannot subtract.
It's also a bright location, reasonably bright when the other slit was open. But when both are open, it becomes dark.
So that's what his assertion is. And again, this is 300 years after Newton. He's making this assertion, and he really doesn't have any experimental evidence to prove that. He can't show it, because if you actually do the experiment, like I said, I showed that in the other 2 videos, you'll see that when you oversaturate, you won't see these dark spots. And if you undersaturate, that is, you lower the light, you won't see the underlying pattern when you only have one of the slits open, because not enough light's going to be coming out of it. Not enough to see.
You can ask, how can it be that I open 2 windows, the room gets darker? Why doesn't it happen there, and why does it happen here?
It doesn't. Okay, so again, there's just no evidence for it. I'm just saying he's just forcing it to say something the evidence doesn't say. It's just a wrong assumption. and it's kind of foolish, and it shouldn't really happen, right? Physics should be like, again, just the way he drew these two lines, like they were in different places or locations in space when they're exactly on top of the same space, essentially 1 millimeter difference. He drew 1 millimeter difference as this huge difference. These are mistakes that just shouldn't be made.
The answer is that you're sending light of definite wavelength,
The video.
and the wave function psi, whatever measures the oscillation, maybe electric field, magnetic field, obeys the superposition principle. And when two slits are open, what you're supposed to add is the electric field, not the intensity. The intensity is proportional to the square of the electric field. You don't add E squared, you add
you
E.
didn't see
E is what
the
obeys the
drawing.
wave equation. E1 is a solution.
So I don't know. Did you see this drawing I did? Yeah. So I drew, these are the 4-point sources, the fact that this wave here, I don't know, did you see any of that? Well, here's the image that goes with what I was talking about. So I don't know how the camera got turned off. I don't know when I did that. Anyway, sorry. Not perfect production skills in this video. Yeah, sorry. Really don't want to do it over again.
E2 is a solution, E1 plus E2 is a solution. No one tells you that if you add the two sources, I1 plus I2 is going to be the final answer. The correct answer is to find E1 plus E2, and then square that. But when you do E1 plus E2, since E1 and E2 are not necessarily positive definite.
So again, he's talking as if this wave mechanics actually produces the right pattern when it doesn't. So again, it's just more talking about two spherical waves interfering, and he can't draw the actual interference that creates the right pattern in the right envelope. It doesn't work.
When you add them, sometimes they can add in the same sense, sometimes they can add with opposite signs, and sometimes in between, so you get this pattern. So we're not surprised. And I told you many times why we don't see it when we open big windows.
Where, yeah, they're not surprised, but again, they're trying to mine the evidence to support the theory. So they'll say, oh, look, it happens with water. That's right. I mean, with water, you can actually do this silly idea where if I open one slit, a boat will be agitated. And I can actually open the second slit and make the water calm where the boat is. Okay? So I can actually change what's going to happen at the location. But that's because the forces are interacting with each other in the medium. So they're already changing as they're getting to the location. And the real truth is the light experiment demonstrates a different pattern because they can't change in the medium. The forces have to get to a location before they can be added up or subtracted. They can't do it in space. Forces don't interact with forces. Light doesn't interact with light. I can't shoot laser beams at each other. I can't shoot any kind of light in any experiment. They can never make light interact with light. And this is the only way they can pretend that it happens.
First of all, when you open a window, the slit sizes are all many, many, many million times bigger than the wavelength of light. Plus the light is not just one color, and so on. So you don't pick up these oscillations. These oscillations are very fine.
Right. So now they're very fine. They're very tiny. They're tiny, 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 tiny. And then he'll talk about the slit widths and the dimensions of the slit as being somehow the wavelength of the light, when clearly they can't be. Because, yes, there's 1 million nanometers across here. This is a millimeter. There's 1 million nanometers worth of space across here. 500 nanometers, you can do that a lot of times going across here. So these slit widths are many times the wavelength of the light, 1,000 times more than the wavelength of the light. I don't know why they keep saying the slit width the same as the wavelength. It's nowhere even close.
Draw them this way so you can see them. In a real life thing, if this were really windows and this was the back wall of your house, the oscillations will be so tightly spaced, I'll just draw some of them, that the human eye cannot detect these oscillations. It'll only pick up the average value. The average value will in fact look like I1 plus I2. So this is all very nice. This is how Young discovered that light is a wave by doing it.
Yeah, okay, so again, and with crude technology, not even seeing the right pattern. So without even seeing the right pattern, he's saying he proved it.
Interference, I told you he could even find the wavelength because it's a simple matter of geometry to see where you got to go for two guys to cancel. Then once you know that angle, you know where on the screen you will get a minimum or a maximum. So you got the wavelength. He didn't know what was doing it. He didn't know it's electromagnetic, but you can get the wavelength. So interference is the hallmark of waves. Anyway.
Well, I think he did because Young was after Maxwell, I think, wasn't he? 1800. No, Maxwell was 17 something or other, I think. Well, anyway.
Will do interference. Water will do the same thing. For example, this is your beach house. You got some oceanfront property. This is a little lagoon, and you have a wall to keep the ocean waves out of your mansion. And then suddenly, one day, there is a break in the wall. Break in the wall, the waves start coming in, and you're having a little boat here, trying to get some rest. Boat starts jumping up and down because of the
Same example. Good.
waves. So you have two options. One option is to go and try to plug that thing. But let's say you got no brakes, no motor, no time, no nothing. You just got a sledgehammer. What you can do, you can make another hole. If this water waves are a definite wavelength, only in that case, you can make another hole so these two add up to 0 where you are. Similarly, if you don't like the music your roommate's playing, if you can manufacture the same music with a phase shift of pi, you can add them together, you get 0.
Right. So we're just stuck with this. They're going to keep saying that everything's the same thing when everything's different. We know the atoms are in pressure between atoms is a different theory than the motion of electrons, and the motion of electrons is a different theory than photons. They're all different physical objects, and they're trying to force them to be the same. And they're forcing it. Like I'm pointing out, they're forcing it by pretending the real pattern isn't the real pattern, by pretending that Huygens works when it doesn't work, and you can't apply it consistently. It fails to work.
0. But you got to figure out what the roommate's about to do and be synchronous with the person, but get a wavelength of pi. I mean, a phase shift of pi. So you can cancel waves. That's the idea behind all kinds of noise cancellation. But you got to know the exact phase of the one signal.
You can cancel signals where there's a material substance that's being agitated, because physical objects can interact with each other and cancel their motion, but forces can't be canceled. Sound isn't a force. Water isn't a force. It's moved by forces, but it isn't itself moving a force.
That you're trying to cancel. All right, so everything looks good for Maxwell till you start doing the following experiment. You make the source of light, whatever it is, dimmer and dimmer. Okay? So you may not be able to turn down the brightness. Maybe you can, maybe you cannot. But you can imagine moving the source further and further back. Okay? You move it further and further back, you know the energy falls like 1 over r squared. So you can make it weak. So here's what we try to do. We put a new photographic film. We take the light source way back. Then we wait for something to happen. We come the next morning, we find there's a very faint pattern that's taken place overnight because the film got exposed all through the night. Now you can see a faint pattern. Then you go and turn it down even more. Then you come back the next day, you look at the film, you find no pattern, just 2 or 3 spots which have been exposed.
All right, so we have another underdone experiment. So something that's another assumption made about function where they didn't prove it with actually doing the experiments. So the idea is the single photon. And again, what would the single photon be? Even by your wave theory, it has to be something of a certain length, okay, to be called a photon. So it has a certain elements to it that it has to contain. And we know that it has this polarization. It has a certain size. And if I break the polarization, if I don't allow the polarization to fit through something like a polarizing filter, that I've somehow degraded the photon. I mean, the photon isn't going to be visible anymore. That's what the photographic polarizer shows you, right? The polarizer is bars. You send the polarized light through it, and based on its polarization, it doesn't make it through. Its polarization, it cuts too many bars and it gets X'd out and it doesn't make it through. And only if its polarization is in line with the bars does it get through the bars. Now they have it exactly the opposite because they're using their stupid, electric field nonsense. So they actually have, they actually think the light getting through is going this way across the bars, because they think going this way means you hit the bars. I mean, it's really silly that they have that even backwards. I mean, they couldn't get plus and minus right, and they couldn't get polarization right either. But regardless, the point is it has these facts to it, and so we're saying, okay, we're gonna try to send just one of these. Well, how do we know we sent one? Well, we can only know by what we receive, right? What is put back together again. So if it is actually a composite and you can actually break it and remake it, And again, the 3 polarizing filters prove my point, right? Because you put 2 filters this way, no light, right? So if I put a filter this way and a filter this way, no light. But if I put another filter in between going this way, all of a sudden I get back, okay, 30% of the light. I put another filter in. I shouldn't be able to get more light by putting a filter in. By putting an obstacle in, I'm getting more. Well, if you understand that all this filter did was change the phase, that is, it took things that were in this phase and it broke the phase, that is, it moved a piece here, right? And so now the frequency is broken because one of the pieces is out of alignment. So one of your waves, whoops, goes a little bit funky, and then you have your regular waves. Obviously, if I put it through a filter that unfunks the broken wave, I can build my photon back. So all we're doing is changing the phase. These are just thin, transparent films, and so if you put 2 films on top of each other, you can have a film that has 1 layer, and then you put a second layer in certain locations, right? You can see that? Yeah. So I put another layer, right? So I have 1 layer, and I put a second layer on top of it in little bars. Well, then this 2x polarizes, this only 1x polarizes. So obviously what you can do is you can 1x polarize, that is, some of the bits will get put to the wrong location, but the second filter will repolarize these, so they'll move these bits forward, okay, or backwards, however you want to look at it, and recreate the original phase by causing a 2x shift here. So this one only gets 1x shifted, this one gets 2x shifted, so it gets back and forward, and they're back in the right order again. And so that's how I can reconstruct the photons. So the photons weren't destroyed by the filter, they were only broken by the filter, and you just reconstruct them, rephase them again, put them back in the right phase, and now they can get through the second filter, third filter. Some of them can get through, so you'll get back some percentage. So, like I said, what I'm saying is consistent with the other experiments. So back to the point here, where we are at the point where he's talking about what did he just say? Oh yeah, a single photon. So what the hell is a single photon? We really don't know. And so the real experiment to do is to have your source of light, have whatever it is that's 1 photoning it for you, you know, some barrier or some obstacle that's hard to get through and only 1 photon gets through at a time. And you put your film here and you just measure how much light you get, how much light actually hits this thing. So you want to get it so it's really a little bit of light. So you say like maybe 1,000 photons a day, you know, and that would be kind of safe. You know, they couldn't be coming at the same time if there's only 1,000 of them in the whole day. There's very rarely there'd be 2 of them coming at the same time through the hole, you could argue. But you don't know what they're going. When they're going through the hole, they might have to require 2 photons to make 1 photon, so they might be broken pieces. But anyway, the point is to reconstruct, you'll be pretty safe. And then put your 2 slits in. And now see if any photons show up over here. And my argument would be is if you're down to 1,000 a day here with photographic film, once you put these slits in here, you're done. You're not going to get any light. There'll be no light received here. And that you'll have to increase you'll have to allow more photons to get through to start receiving light over here. So if they did the experiment in the right order, had the control first to figure out how many photons am I actually getting an hour, and then put the slits in, then they'll have the intensity at the right intensity to see if I've eliminated the 2 photon phenomenon. Because frankly, they're going to have to be more than 1 photon for you to get the pattern. It's just not going to happen. Their own geometry essentially proves it. You have to have the contribution from here, and you have to have a contribution from here, and you have to have a contribution from here, and you have to have a contribution from here. And you can only have those contributions if you have more than 1 photon hitting these surfaces at the same time. You just don't have any hope otherwise. And if they did these experiments in the right order, they could prove or disprove. They could establish enough evidence to say what they're saying with some authority. But they haven't done these simple experiments. Instead, they waste trillions of dollars, billions of dollars, many billions of dollars on Higgs bosons and LIGO gravity waves and all kinds of other silly satellites they're going to put up there doing all kinds of silly shit. instead of doing this and actually establishing that you have a reason to say you've proven something.
You look at the screen. So let me show you this view of the screen. Normally, you will have bright and dark patterns on the back wall if you turn on a powerful light. But I'm telling you, if you have a really weak source, you just find that got exposed, that got exposed, and that got exposed. That's it. Only 3 points in the film are exposed. And that is very strange, because if light is a wave, no matter how weak it is, it should hit the entire screen. It cannot hit certain parts of it. Waves don't hit certain parts of it.
Right. So he's clearly not thinking of waves. You know, see, this is another argument. Like the dumbasses think that when they actually draw a wave like this, they're actually saying photons are doing this through space. When that's not what they're saying. They're saying there's an amplitude, okay, that these are amplitudes. But it has nothing to do, it's like a pressure, you know, and the pressure is spread over the entire area. So when they draw this, they're really saying this, you know, they're saying this whole spreading thing is happening. So these humps just represent the spreading of the wave, and that the wave doesn't actually oscillate up and down, that it actually just moves through space.
In fact, how can it hit just one? For example, if you make it weak enough, you can have a situation where in the whole day you just get one hit. So something is hitting the screen and it's not a wave, because the wave is spread out over its full transverse dimension, but this is hitting 1 point on the screen. So you make further observations, and you find out that what happens here is that a certain amount of momentum and energy are delivered during that hit. If you could measure the recoil of that film, you will find it gets hit, and the momentum you get per hit looks like h bar times k. I'll tell you what it means. This is 2 pi h over lambda. Well, lambda is your wavelength. H is a new constant called the Planck's constant, and its value is 6.6 times 10 to the minus 34 joule seconds.
So this is where they're going to turn frequency into momentum when they're not the same thing. So obviously the little bits have momentum. When you have 6 little bits, you have enough momentum to say there's a photon, but the little bits obviously have to be in the right order. So if you don't have them in the right frequency, if they're inconsistent frequencies, if they're inconsistent distances from each other, you won't receive it as a photon, just like you can't receive it on your radio, a signal that's broken like that. So it has to be consistent, the frequency. Well, FM's a little different because you're catching a whole band of signal. So you can change the frequency a little bit and it's okay, as long as your receiver is receiving a wide band of frequencies. But in most cases you can't do that. Well, there's certainly limitations to how wide the band can be. Just like you can see all of the wavelengths of light, or you could filter just so you see certain wavelengths. You know, you can create limitations, but there's only so much you can do. We can't see all of the radiation, just like we can't see all of the bands of radio frequency. We can't just create a detector that picks up any frequency. All frequencies at once. It has to be tuned to pick up frequencies. All right, so yeah, so he's pointing out that it can't be this wave thing because it doesn't spread over an entire surface, although the momentum's hitting one location. But again, it's not one tiny location in the sense that it's an area of a bunch of atoms, and that's what the photographic film sort of demonstrates. It's a whole clump of atoms that have to switch. You can't make the photographic paper one, you know, you can't make a bunch of tiny little atoms and just have the atoms flip. It has to be a whole row of atoms to flip. And so this is a process that happens because light hits more than one atom. The energy of the photon is hitting more than one atom. It's not hitting one electron. It's not vibrating one electron. It's vibrating electrons in a series of atoms. And the fact that we can't make photographic paper finer and finer and finer is sort of proof of that this isn't something that happens to just one atom on a surface. It's a little clump of atoms. But again, atoms are so much smaller than the wavelength of light. The wavelength of light is huge, you know, the polarization, compared to the size of an atom. 2,000 atoms worth of wavelength. All right, so we may well end here, 11, 12 minutes, so I'll remember that, and do a part 2 and 3 and 4. But you can see he's building up this argument between this wave-particle duality. So he's argued that yes, waves were proven, and now he's arguing, okay, particles have a lot of evidence, and so now he's trying to force this idea that depending on how we want to look at it for a particular cause or purpose, we can think about it as a particle or think about it as a wave. And it's just this idea, this isn't about what you're thinking about. It's not about how you're interpreting it. It's about what it is. And that's not a reasonable answer to say it's both, because it can't be. Because they're two fundamentally different things. And there are explanations, as I'm providing, where, yes, they're particles. Particles can look like waves, but they don't act like waves. Okay. Then my job, that's all I can do, is reason with you, just explain why you shouldn't trust these people. Again, I've shown him doing things that are just wrong. And it's the simplest, and it's a cornerstone experiment. This is a cornerstone to their entire theory. These things he's asserting as truth being true. And they're not true. That should give you real pause to think, why am I believing that these people know the truth or have the right idea when they can't even describe their cornerstone experiments accurately? All right, now it's enough. And such.